Welcome everyone. Today, we'll be diving into an interesting coding problem titled Find 3 consecutive integers that sum to a given number. We'll explore the problem statement, break it down step by step, and look at possible approaches for solving it. Let's get started. The problem is asking us to find 3 consecutive integers that add up to a given number. Consecutive integers mean numbers that follow each other directly, like 10, 11, and 12. If such integers exist, we return them as an array in the form x plus 1, x plus 2. If it's not possible to find 3 consecutive integers with a sum equal to number, we return an empty array. For example, if the input number is 33, we should return 10, 11, 12, since 10, 11, and 12 add up to 33. This problem requires us to handle numbers ranging from 1 to 10 to the power of 15, so we need to think about efficient ways to solve it given such a large input range. Here's why the output, 10, 11, 12, is correct for the input number equals 33. The solution identifies 3 consecutive integers, 10, 11, and 12, whose sum is 10 plus 11 plus 12, resulting in 33, which matches number. Now, consider the case where number is 4. Here, no 3 consecutive integers can add up to 4, so the function returns an empty array. This demonstrates that the solution not only identifies valid sequences when they exist but also handles cases where a solution is not possible. For the input number equals 0, the output is -1, 0, 1. These are 3 consecutive integers, and their sum -1 plus 0 plus 1 equals 0, which satisfies the given condition. This example highlights that the solution works for inputs where number is 0 and can include both positive and negative numbers in the output. Additionally, the constraints of the problem clarify that the input number can range from very large negative values to very large positive values, so handling precision becomes important. The output must always consist of exactly 3 consecutive integers or an empty array if no solution exists. The constraints further emphasize that the 3 integers must form a sequence, such as x plus 1, and x plus 2. This means the numbers must follow each other in order without gaps. For edge cases, the solution must handle extreme values, like number equals 10-15 or number equals -10-15, efficiently. It should also address smaller values, such as number equals 0 or number equals 1, ensuring correctness in these cases. When no solution exists, such as when number equals 4, the function must reliably return an empty array. By addressing these edge cases, the solution ensures robustness across the entire input range. To solve the problem of finding 3 consecutive integers that sum to a given number, we considered a few different approaches. The first and most straightforward option is the brute force approach. This involves iterating through possible sets of 3 consecutive integers, calculating their sum, and checking if it equals the target number. For example, we would evaluate sets like x plus 1, x plus 2, where x starts from a small integer and increases. However, there's an important insight here: the sum of 3 consecutive integers can be expressed as 3x plus 3. This means that, instead of checking random sets, we could limit our search to numbers up to approximately number/3. Still, this approach is inefficient for larger inputs because it involves iterating through many values unnecessarily. The time complexity is O(n), where n represents the range of values we need to check, and the space complexity is O(1). While brute force can work for small inputs, it's suboptimal because the problem's structure allows for a much simpler, direct solution using a mathematical formula. Now, let's explore the optimized mathematical approach, which takes advantage of the equation for the sum of 3 consecutive integers, x plus 1, plus x plus 2, equals 3x plus 3. By rearranging this equation, we can solve for x as number 3/3, or equivalently, x equals number/3, 1. This tells us that x is only valid if number 3/3 results in an integer, which happens when the given number is divisible by 3. From here, the steps are straightforward. First, we check if number %3 equals 0. If it's not divisible by 3, we can immediately return an empty result, as no solution exists. If it is divisible, we compute x as number/3, and return the 3 integers, x plus 1, x plus 2. The efficiency of this method is remarkable. The time complexity is O(1), as it involves a simple divisibility check in basic arithmetic operations, and the space complexity is also O(1), since no additional memory is used. This approach is optimal because it directly leverages the mathematical structure of the problem, eliminating unnecessary computations and ensuring correctness in a concise, efficient manner. When considering trade-offs and alternative approaches, we found that other methods, such as binary search or iterative techniques, were redundant in this context. These approaches add unnecessary complexity without improving efficiency, as the mathematical solution already solves the problem in constant time. Similarly, while recursion could technically be used to simulate checking sums, it would be computationally expensive and overly complex for such a straightforward problem. Ultimately, the chosen strategy is the optimized mathematical approach for its simplicity, elegance, and unparalleled efficiency. By directly calculating the solution with arithmetic operations, we avoid the overhead of loops, recursion, or additional data structures. This guarantees that the answer is found or determined to be impossible in constant time, making it the most effective solution regardless of input size. The problem requires us to find 3 consecutive integers whose sum equals a given number. To approach this, we start by representing these integers mathematically as x, x plus 1, and x plus 2. Adding them together gives us x plus 1, plus x plus 2, which simplifies to 3x plus 3. For this sum to equal number, we derive the equation 3x plus 3 equals number. Rearranging this, we find x equals number 3/3. This equation forms the foundation of our solution, as it provides a way to calculate the first integer, x, if it exists. The key insight here is that solving this equation will help us determine whether the 3 integers are valid and what their values are. Next, we need to confirm whether x is a valid integer. For x to be an integer, the value, number 3, must be divisible by 3. Mathematically, this means, number 3% equals 0. If this condition is true, we can calculate x using the formula x equals number 3/3. Once we have x, the 3 consecutive integers can be determined as x, x plus 1, x plus 2. This approach ensures that the solution is both efficient and straightforward, relying solely on simple arithmetic and divisibility checks. If the condition, number 3% equals 0 is not met, it means that no such integers exist, and we return an empty list. It's also important to consider edge cases, such as very small values of number, including 0 or negative numbers, as well as very large values. Regardless of the input size, the solution remains efficient because it operates in constant time. The result will either be a list of 3 integers or an empty list. This efficiency comes from the fact that the problem is reduced to a simple mathematical check, avoiding the need for loops or complex data structures. The space complexity of this solution is O(1), since no additional space is used beyond a few variables. To illustrate this approach, let's walk through an example. Consider number equals 33. First, we check the condition, number 3% equals 0. Substituting the value, we find 33 to 3% equals 0, which is true. Then, we calculate x using the formula x equals number 3/3, resulting in x equals 10. The 3 consecutive integers are therefore 10, 11, 12. We return this list as the solution. Now, let's look at another example with number equals 34. Checking the condition, number 3% equals 0, we find 34 to 3% equals 0 is false. Since this condition isn't satisfied, we return an empty list. For an edge case like number equals -3, we calculate x as -3 to 3/3 equals -2, yielding the integers -2, -1, 0, which form a valid solution. The final implementation of the algorithm is simple and concise, as shown in the code. It checks the divisibility condition, calculates x if valid, and returns the appropriate result in constant time. This Python implementation solves LeetCode problem number 2177. Find 3 consecutive integers that sum to a given number. The function sum of 3 determines if the input number can be expressed as the sum of 3 consecutive integers. The 3 consecutive integers can be represented mathematically as x, x plus 1, and x plus 2. Their sum is given by the formula 3x plus 3. To find x, we rearrange the equation, number equals 3x plus 3, leading to x equals, number 3/3. For x to be a valid integer, number 3 must be divisible by 3. The function first checks this condition using the modulus operator, number 3, %3 equals 0. If the condition holds, it calculates x as number 3/3 to ensure integer division and returns the three consecutive integers as a list, x plus 1, x plus 2. If number 3 is not divisible by 3, the function returns an empty list, indicating that no such three consecutive integers exist for the given number. This solution is efficient, with a time complexity of 1, as it involves only a few arithmetic operations and a constant number of checks. This makes it suitable for very large input values of number, as long as they fit within the constraints of the problem. This is the Java implementation of LeetCode problem number 2177. Find three consecutive integers that sum to a given number. The logic is identical to the Python implementation. The method checks if the input number can be expressed as the sum of three consecutive integers using arithmetic calculations. If valid, the three integers are returned as an array, otherwise, an empty array is returned. Java-specific elements include type declarations, the use of arrays instead of lists, and the explicit long type for handling large numbers. To solve this problem, we need to find three consecutive integers whose sum equals a given number, represented here as number. These integers can be expressed as x plus 1, x plus 2. To start, we derive a formula based on their sum. Adding these three terms together gives us number equals x plus 1, plus x plus 2, which simplifies to number equals 3x plus 3. Rearranging this equation to solve for x, we get x equals number 3/3. Now, for x to be an integer, it's essential that number 3 is divisible by 3. This condition ensures that the division results in a whole number, making it possible to find valid consecutive integers. With this framework in mind, we can test it using specific examples to better understand the solution process. Let's consider our first example where number equals 33. To start, we check whether number 3 is divisible by 3. Here, 33 to 3, %3 is equal to 30% 3 equals 0. Since the result is 0, we know that number 3 is divisible by 3, so we can proceed to calculate x. Using the formula x equals number 3/3, we get x equals 33 to 3/3 is equal to 30/3 equals 10. Now, the three consecutive integers are x plus 1, x plus 2, which gives us 10, 11, 12. To verify, we check the sum of these integers, 10 plus 11 plus 12 equals 33, which matches the given number. Thus, the output is 10, 11, 12. For another example, take number equals 4. Here, 4 to 3, %3 is equal to 1%, 3 equals 1, so number 3 is not divisible by 3. This means there's no valid value for x, and therefore, no solution exists. In this case, the function returns an empty list. Now, let's examine number equals 0. First, we check whether number 3 is divisible by 3. Here, 0 to 3, %3 is equal to -3%, 3 equals 0. Since the result is 0, number 3 is divisible by 3, allowing us to calculate x. Using the formula x equals number 3/3, we find x equals 0 to 3/3 is equal to -3/3 equals -1. The three consecutive integers are x plus 1, x plus 2, which gives us -1, 0, 1. Verifying the sum, we see that -1 plus 0 plus 1 equals 0, which matches the given number. Thus, the output is -1, 0, 1. A few key observations about this approach: it's efficient because it relies solely on simple arithmetic checks and calculations. The condition, number 3% equals 0 ensures that x is always an integer, and when no solution exists, the function quickly returns an empty list without unnecessary computations. This makes the solution both clean and effective. To analyze the time complexity of the solution, we break it down step by step. First, the condition, number 3% equals 0 checks whether the number adjusted by 3 is divisible by 3. This involves a subtraction and a modulus operation, both of which are constant time operations, or O1. If this condition is true, the code calculates number 3 // 3 to determine the base integer, which is another constant time operation. Next, the solution constructs the result list x plus 1, x plus 2, which involves creating a list with 3 fixed elements. Since the size of the list is constant, this step is also O1. If the condition is false, the function simply returns an empty list, which is another O1 operation. Adding all these steps together, every operation in the function takes constant time, so the overall time complexity of the solution is O1. Now let's examine the space complexity of the solution. First, we consider the variable x, which is computed and stored if the condition is true. This requires a fixed amount of memory, or O1 space. Next, if the condition holds, the solution creates the result list x plus 1, x plus 2. This list has a fixed size of 3 integers, so it also requires O1 space. If the condition is false, the function returns an empty list, which again requires a constant amount of space. Importantly, the solution does not use any additional data structures or perform memory-intensive operations. With these considerations, it's clear that the space usage remains constant regardless of the input, resulting in an overall space complexity of O1. Let's compare this approach to a brute force method. A naive solution might involve iterating through integers and checking whether 3 consecutive integers add up to the target number. This would involve a loop, performing repeated checks for each potential starting point. As a result, the time complexity of the brute force approach would be O(n), where n represents the range of integers considered. While the space complexity would still be O1 for variables, this method is computationally inefficient. By contrast, the current solution eliminates the need for iteration entirely by leveraging the equation number equals 3x plus 3. By solving for x directly through constant time arithmetic operations, it efficiently determines the result. This reduces the time complexity to O1, making it significantly faster than the brute force approach. Finally, since all operations like subtraction, modulus, integer division, and constructing fixed-size lists are constant time operations, the time and space complexity for this solution are both conclusively O1. When solving this problem, there are a few common mistakes to keep in mind. First, it's easy to overlook integer constraints. For instance, dividing the input number by 3 without ensuring that the result is an integer can lead to incorrect solutions. Always check if the number is divisible by 3 explicitly. Another frequent issue is off-by-1 errors when calculating the consecutive integers. For example, starting at n1 instead of n can throw off the entire solution. Additionally, some solvers tend to overcomplicate the problem by using loops or recursion, which are unnecessary here since there's a straightforward mathematical solution. It's also important to consider edge cases, such as when the input number is very large, very small, or negative. For instance, if the number is less than 3 or not divisible by 3, the problem constraints might not be satisfied. Lastly, be cautious with floating point arithmetic. Using floating point division instead of integer division can introduce precision errors, so it's better to stick with integer operations for accuracy and simplicity. A key insight for this problem is that the sum of 3 consecutive integers is always divisible by 3. Mathematically, the formula is n plus 1 plus n plus 2, which simplifies to 3n plus 3, or 3n plus 1. This means the input number must be divisible by 3, and if it is, you can calculate n as number divided by 3 minus 1. Recognizing this pattern is critical because it highlights the mathematical structure underlying the problem, which is a useful skill in technical interviews. Additionally, interviewers often expect you to discuss edge cases and analyze the time and space complexity of your solution. Here, the direct mathematical approach runs in constant time and space, making it highly efficient. As a follow-up, you might be asked to extend the solution to handle k consecutive integers. In that case, the formula generalizes to k asterisk n plus k, k1/2 for the sum of k consecutive numbers. Being prepared to adapt your logic to such variations demonstrates a deeper understanding of the problem. This problem shares similarities with several related problems that focus on sum-based techniques. For example, LeetCode problem 1, 2 sum involves finding two numbers that add up to a specific target. Similarly, LeetCode problem 1074, number of submatrices that sum to target, extends the concept to finding subarrays or submatrices with a given sum. Another related problem is LeetCode problem 560, subarray sum equals k, which requires identifying continuous subarrays that sum to a target value. Finally, LeetCode problem 216, combination sum 3, asks for combinations of numbers that satisfy a target sum, which ties closely to the sum of integers pattern seen here. Exploring these problems can help you build a stronger foundation in solving sum-related challenges and recognizing patterns that emerge across different scenarios. There are several approaches to solving this problem, each with its own trade-offs. The optimal solution is the direct mathematical calculation. By using the formula for the sum of three consecutive integers, you can check divisibility and calculate the integers directly. This method is highly efficient, with constant time and space complexity. However, it's tailored specifically for three consecutive integers. If you need to handle a variable range, such as k consecutive integers, you'll need to generalize the formula accordingly. Another approach is iterative search, where you loop through potential starting numbers and check if their sum equals the input number. While this method works, it's significantly slower with linear time complexity and is harder to justify in an interview scenario. The least efficient approach is brute force, where you generate all possible subarrays of size 3 and check their sums. This has quadratic time complexity and is completely unnecessary for this problem. Understanding these approaches and their trade-offs can help you choose the most appropriate solution based on the problem constraints and context. Great work! To wrap up, we reviewed how to solve the problem efficiently using a mathematical approach with constant time and space complexity. Remember to practice leveraging problem constraints to simplify your solutions. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!